All right, guys, let's get started. Okay, so today we're going to continue with last week's lecture. Um, so if you remember, we were looking at just an understanding of the training algorithm, okay, on deep learning. So we're going to continue with that. I'm going to go to let me actually just make sure. But we should be recording here. So I'm going to go to the GitHub. All right. So we were in, so you guys can't see that. I'm sorry. There we are. So we're going to go to deep learning algorithms, the GitHub, second edition. And we are here, traditional machine learning. So if you remember last week, we were looking at some of the background. So we looked at examples of curve similarities, normalized losses, and I believe we started with Scratch gradient losses, torch NN. So this was basically looking at the gradients calculation, right? So we did a couple of examples of that. And today I'm going to do a few more, right? Just to kind of drive the idea of what PyTorch is doing in the background. And then we're going to do an optimization learning from scratch. We're basically going to train a model to predict Fahrenheit given Celsius or something like that. And so it just kind of goes over that. So that's sort of the background. And then that's my plan for today. And then also, as one of the traditional algorithms I will cover is k-means. And basically we'll go over just an unsupervised method really quickly. And actually it's important because I'll cover several ideas there about embeddings. We'll be using text kind of related to the GPT. And then we'll use something like the one-hot encoding approach, and then that leads into embeddings, which is pretty central to deep learning currently. All right, are there any questions before I begin? Here's the sign-in sheet. So please sign in and pass it around. Any questions on the homework? I know we have a homework assignment that's due, I think, next Monday, right? So yeah, any questions on that? So you have to train your GPT. The model should work, but you have to collect your data, your text data off the web, right? So you're scraping, I assume, this type of a competition thing very quickly, see who builds the best vet GPT. All right, and we're going to see how that would work. And the winner will win a trophy. All right, a 3D printed. All right, are there any questions on that homework assignment? Was everything clear there? Yes. Yeah. Yeah, that's a good question. So qualitatively, probably, unless anyone can think of some quantitative metrics. So it's kind of tricky, right? Because is it fair? But qualitatively, certainly, we'll just ask a question, see the relevance of the question of the answers. Does that make sense? It's certainly something to think about, right? So the whole point of this mini project, if you will, is to think about, all the challenges with it and train it with scraped data. No further questions? Everyone good with that? So if you have any issues, email me. See me during office hours, But yeah, so we'll talk about it next Monday, and then from there we'll start scheduling some presentation. Okay, it'll be quick presentations just to see how it performs. Obviously, you want to run it sometime, right? Either like creating a demo or run it in real time. So either one is fine. Got it? Does that make sense? Like in a Zoom session, you can create your model. I trust you guys that you're not using ChatGPT in the background. All right, so it seems there's no questions, right? So, all right, so now we're going to continue then with, like I said, what we did before last week. So I should have my Jupyter notebook here. I'll just try to find the one that I used last So, and then we're going to continue. So what are we discussing? The derivatives, which are the gradients and the chain rule. Just to take a look at that, I'll do a very simple example on the whiteboard or two. And then from there, we'll train a model from scratch just so that you guys can see the basic ideas of what's going on in the background. Okay. And remember, this is still, we're going to be using MSE. I still need to do cross entropy. So there will be one last loss example of cross entropy for classification. But we need to cover a few more things there. Also, before I forget, we are currently on week 11. So what do we have a week from today during the last half of class? Exam 2, right? So don't forget, during that second half of class, you'll have exam 2. And hopefully today I'll be finished with a lot of these topics. So we'll be basically cover the last part of the class, which is more like the image-based ideas that will include like a CNN, stable diffusion, and those basic embeddings. So kind of the final part of everything. All right. So I'm going to go ahead and navigate to my desktop. All right, so we are 5/20, 2024. There we are. There. And we were working on, I think it was learning ideas, I want to say. DIR. Right, so we were doing normalized losses, in-class learning examples, autodiff torch. So maybe autodiff. Do you guys remember if it was autodiff? Right, so conda environment list. I just want to pick up where I left off. Conda activate. I think it's I38 ML 2024. All right. So Jupyter notebook. And any issues with Scholar? Did everyone try Scholar? Right? Have you guys tried Scholar and it works? Okay. Yeah, so you can ask Henry Olson if you have issues, but everyone should try their account, make sure that you have Scholar as you're going to need it, right, for your homework assignment. All right, so let's start. I think it was this one, autodiff. Yeah, I think it was this one, gradient. Right, so we did, the last problem we did was this one, if you remember, right, X and Y. So I'm going to do a slightly more complex one with 3 functions, probably X, Y, and Z, right? And then we're just studying this idea, hopefully, of what Torch is doing in the background. So I'm going to go ahead to my GitHub. So the code should be here. And then from there, we should be able to write the learning algorithm from scratch, basically, and see its behavior. So, okay, so we did, yeah, we haven't done this one, I believe, but we did this one. Oh, yeah, we did this one. We did this one too, right? So y equal x squared and z 2y plus 3. Okay, so we've done that one. All right, so we're going to do another example, the third one. This one. And another, what I'm going to pick up here This one's a little bit more complex as far as the chain rule, but hopefully you can see how this one allows you to calculate the derivatives for multiple weights, not just for one weight. So imagine A and B here are going to serve as weight 1 and weight 2. And kind of what would be going on in the background to do the update rule in PyTorch, right? So that's kind of the idea to explore these things. And then we'll drive it down to the end. Remember that this is in the context of a computational graph, right? Which is what we're running in the background, okay? So I'll do another example here. So this one requires a little bit more like notation. Okay. So here is the example starts with these functions over here. So these are the functions. Remember, this is one function feeds into another function and so on, but we're going to treat A and B as the two things that we want to have graph. Okay, so I'm going to go ahead. And remember, we have these functions, but we're going to need to calculate them in terms of one of the variables. So in this case, we're going to calculate them in terms of A. And so therefore, when we have the function, then we take the derivative of that function in terms of the letter, the weight that we're trying to update. And then when we run the data through the derivative of it, we get a specific value. And we're just going to corroborate that the analytical solution is equal to the PyTorch solution, which is what I've been doing, what I did last week as well. But this is a slightly more complex one. All right, so let's think about this one. So I'm going to write this on the whiteboard. So let me open it here. All right, so I have it here. All right, so let's go ahead and switch over to the whiteboard. Okay. All right, so switch color to red. All right, so we have the functions x, which is 2a plus 3b, right? And just keep in mind, this a and b are going to be like our weights. Think of it as the weights, the thing that we want to, take the derivative of at a specific point in time so that we can calculate what that value would be. And then based on that, we can update our network, okay? So that's kind of what we're going to do. Then we have y, which is going to be 5a squared, okay, plus 3b to the 3, right? So cube, and then z, which will be 2x plus 3y. Right? So this is our function. This is actually the function. And then we need to have this is like you build a neural network. As it's training, we would take that function and calculate the derivative of it in terms of one of the variables, A or B. So that's why in the example, you see these derivatives. So here I'm going to do d of z in terms of x, okay? And then we're going to see d of z in terms of dy. And then we're going to have d of x in terms of a, and d of y in terms of a. So this is like what's happening in the background, all right? This is what Torch does. Thankfully, we don't have to do this, right? But this is what Torch does for the function that we have. So we have the derivative of z in terms of x. So this would be 2, basically. 2. And again, if you don't know calculus, that's fine. But just keep in mind, there's an operation that has to happen from the original function to the new function, right? And that's, we use the derivative. And the reason why we use the derivative is that it has a specific information that it gives you. When you have a function and you take, a type of derivative of it, you get this information that you can later use, right? And this is one of the innovations of stochastic gradient descent. All right. Then I'm going to do d of c of y, and that should be 3 here. So you're just taking the derivative. So the derivative of 2x is 2. The derivative of 3y is 3, and you treat the rest as a constant, right? So that's basically the idea. So then you do the derivative of x in terms of a. So the derivative of x in terms of a, that's going to be 2. And finally, the derivative of y in terms of a, and that's going to, so this one, and that should be 10a. Because it's going to be, 2 times 5 is 10, and then this is 10a. Again, this is a nice exercise that I leave for you guys to do, kind of for your own intuition. How do I take the derivative of these things? There's specific rules that you follow. But what's important is you built a neural network, right? This one over here. That's what you build in the architecture, in the computational graph. PyTorch then, every time that it's training, it looks at it and it needs to calculate these things that you see here. Now, this is a very tiny network. Imagine if it were like a GPT or something really massive, right? So that's going to be a lot of computations. So this is something that, you had to have some kind of a solver that was very powerful to do this. And that's why we need tools such as TensorFlow or PyTorch. Okay. So once you have these derivatives, then you kind of have to think about the computational graph and how it works. So you have to put them together. So in this case, we have, we're going to have, so the computational graph starts at C and connects X and Y. And then this Y is connected to A and B, and this X is connected to A and B. So you have to think of it as a computational graph. So we're going to look at it in a new graph here, in a new picture. Okay. So I'm going to draw the graph. So I'm going to have Z, and C is going to take in 2x, and it's going to take 3y, and then x is going to take in 2a and 3b. Okay? And then this one will take 5a2 and 3b3. However, since we're only worried about the a's for now, we can ignore the b's, right? So that's what you're going to try to calculate here to arrive at z. So that should be then the derivative of, so this is the so-called chain rule. So the derivative of z in terms of x, which is going to be times the derivative of x in terms of a, plus the derivative of c in terms of dy times the derivative of dy in terms of dA. Do you see that? So this is what's happening in the background that you're putting together, okay? Just for, remember that you calculate the derivatives in terms of a specific parameter, like W1, W2, right? And so on. So these values we've already calculated in the previous graph. Okay, so these should be then, the derivative of c in terms of dx was 2. So we can see that the derivative of c in terms of x was, let me go back. Right, so I calculated these values, right? The derivative of c in terms of x is 2. The derivative of x in terms of a is 2. The derivative of c in terms of y is 3. And the derivative of y in terms of a is 10a. So you calculate these like separately, and then you put them together through this chain rule. You don't need the values for b. Like we don't need, if I close here, we don't need dy of db, and we don't need dx of db, because we're not looking at that parameter right now. We're only looking at the a parameter. We need that information to update that specific weight. Okay, so that's the basic idea. So again, I'm just showing you the process, right? The neural network is here. PyTorch will do this. And for way more operations, depending on the number of variables that are available. Once all of these are calculated, there's this thing called the chain rule, which is the thing on the, guys. All right. On here, we look at the graph, and we kind of ignore the B's, right? Because we're not trying to find information about the B's, currently only the A's. So then the graph becomes kind of this idea called the chain rule. And so then we've already calculated these parameters. So all we have to do is put it together. So as I said, DC, okay. So DC of DX is 2. DC of dA is 2, plus DC of dy is 3, and finally, dy of dA is 10a. Oops, 10a. Okay, so now what you do is, in the computational graph, imagine just gets a new set of values, and you perform the operation there. So I'm going to do this like here. So this becomes 4 plus, what is this? 3 times 10 is 30a. And that's the answer. Oops, sorry. And this is the answer, okay? Does that make sense? So you create the neural network. What is the neural network? A whole bunch of operations, tensors, pluses, multiplications, etc. Whenever you're training, it was discovered by this gentleman who just won the Nobel Prize, right? His name is Geoffrey Hinton, right? To do these kinds of things, right? So this is his Nobel Prize right here. And so what you do is you take that graph, that function, you calculate derivatives in terms of a specific weight you're trying to update. And as it turns out, that gives you this very valuable information on how to update. So instead of updating the weights randomly, we update them by saying adding or subtracting from them, right? And that's what this information is giving you. And this is the so-called gradient calculation. So now we have to remember, so I'm going to take this 4 plus 30a, right? We're going to remember that 4 plus 30a, and I'm going to go back here. I don't know why that keeps happening here. All right, so I'm going to put here 4 plus 30a, right? You guys see that? So basically, this is what Torch gives me. And so now what I can do is evaluate these parameters, and we're going to see the values. So let's go back to our, so we have this calculation. Now let's go back to the code. Okay. All right, so I'm here. So now I'm going to perform the operation. Yeah, this is, yeah, okay. So here, I'm going to say, yeah, another example. Okay. Okay. And so let's put this into action. So let's remember, what was it? 4? What was it? 4 plus 30a? Yeah. Okay. So let's just remember that. And let's go over here. These are all the worked out for your reference, you know, dc dx, dc dA. Notice that I did include dy dB and dx dB, but we just didn't use them. As an exercise, or, you know, not homework, but just for your own, repeat this, but for B. Do you guys see how you could do that? You could easily do that. Repeat the same thing I did, do the calculation analytically, corroborate, and just do it in terms of B. And you would see, yeah, please. Yeah, do you have a question? Oh, okay. Yeah. Does that make sense? So repeat the exercise for B, and that's equivalent to having like a weight 1 and a weight B that you're updating in your network. So now I'm going to go ahead and create the two tensors A and B. So notice over here, I have tensor A equal to 2, tensor B equal to 1, and I plug in requires grad. So that basically is saying that A and B is what needs to have a derivative calculation, which is the operation I just did. And I just showed you kind of how it works. So I'm going to go ahead and run this one. So it's thinking, oh, yeah, so this is the old. I need to load the libraries. Okay, it's taking a second there. Okay, but finished. So now let's go down here. So I'm going to load, and there we go. So I got my two tensors. I will, you know, we don't actually hard code this equation, right? This equation is what Torch like guesses, if you want to say. It solves basically. All I'm going to do is I'm going to write the equations. Just for ease of use, I just kind of made it a little bit simpler, but you can see this is x equal 2a plus 3b, y equal 5a squared plus 3b cubed, and then z is 2 times x plus 3y. So the same thing I wrote on the whiteboard, right? So the same idea. Okay, now the computational graph has been created. You grab z, and z grabs x and y, and this y is connected to this y, and this x is connected to that x. That's the beauty of PyTorch. It creates that whole computational graph for you. All right, so now I'm going to go ahead and do the magic here. All right, so the magic here is basically, instead of doing all the things that I did on the board, right, I just do the derivative calculation here, C backward. And that's basically doing everything so that the gradients have been calculated now for this. We've already provided a value for A, right, which is the tensor 2 over here. Do you see that? So then now when we ask, now the one thing about Torch is it won't give you the equations. Instead, it just kind of stores the value. So it's the one thing that you have to like get used to. So now if I do A dot grad, it gives me the value 64. Where's that 64 coming from? A is 2, right? What do you think? Do you guys understand? Do you see it? So basically, there it is, right there on the board, right? So you create the functions. You create for A, in this case, the value 2, and for B, the value 1. You take the derivative of it, and now the gradient has the value 64. So during training, it basically did that. It took the functions, and it calculated this derivative, applied the chain rule, boom, you have a gradient value. And now you can do the update without a problem. And that's why, you know, I showed you guys that if I started with this equation and I took the derivative of it in terms of A, I arrived at 4 plus 30A. So when I plug in 2 here, 2 times 30 is 60, plus 4 is 64. So this 64 matches this 64, and it's the same thing. Any questions? Does that make sense? So that's, that's what I wanted to show you as far as how this works, right? So this is the famous gradients when you say stochastic gradient descent, right? So you've heard that algorithm, I'm sure, many times. Is, by the way, the only way to train AI models, machine learning models in particular. There is no other, right? There are variants of it, but the idea is this one. Whether you're training ChatGPT or you're training your little neural networks that we did at the beginning of the semester, the exact same algorithm, okay? And so this is key that you understand that this is happening in the background. As an exercise, as I said, I leave it to you guys to try the same thing, but in terms of B, and work out the value, okay? So now, yeah, so that's the example I wanted to cover. And now I think we're done with derivatives, right? So we should be done with derivatives. So I'm just going to go back to the background of stochastic gradient descent. So now we can go. So the question that you want to ask yourself now, you can see in my slides, how does all this relate to training, right? How does it all relate to training? For the previous example, assume the output is Z, right? So we know that it's like a model that we're training, right? We give it some data and we predict C over here, but actually that's not where it ends. There's, the function gets an input and produces an output. But during training, you need to do something, right? To update the weights. And so what you're going to do is you're going to compare the predicted to the real. Okay, so in this case, for the previous example, we assumed that the output is Z. Therefore, there is a corresponding real value, and we're going to call that T, which is, you can call it the label or the regressor. In this case, I'm assuming it's like regression, like temperature, something like that. So then the error now becomes Z minus T squared, right? So we're going to have a model. Imagine this was our model. It takes in some input. It predicts a value Z, and we're going to compare that to the real value. And that becomes now, that information is what we're going to use, right? So that becomes the node that we're going to have in our model. So this C minus T square, call it E. And so now the E is just another node in the computational graph, basically. So that's what you're going to grab. That's usually where the loss comes in. That's the node that's linking the predicted to the real. So it is now effectively dE over dW1. Do you see what I'm saying? So this is how the computational graph is going to interpret everything. So it's going to, because Z is already related to all these equations that we saw before, which is the neural network. T is just your real data, right? So you have that computational graph, and that's the node E, and you can basically perform the same operation I've been doing, just it's going to be dE in terms of dW1 or A, or dE in terms of dB or dW2. Does that make sense, guys? That's it. That's the whole trick with what's going on in the model. All right, so that's hopefully that gives you the background of all these concepts, the chain rule in action, okay, how everything relates to the computational graph. And then basically, as I said, this is just several functions creating a neural network, takes in data, predicts, the predicted is compared to the real. And every time you're training, you have to perform those derivatives that I was showing you in terms of all the weights and do the updates. Okay. All right. So that was like the math of it, right? We obviously don't do that. We haven't, during the first third of the semester, you train models and you didn't do that, right? Because PyTorch was doing that for you. So instead, all we really need to know is backward, right? So if you remember when I gave you the code at the beginning of the semester, I just kind of just do backward and step, and that's it. Remember that? And it was nice. But really what was happening in the background is this, okay? So that's, what I've given you now is an explanation of how when you do this backward, you're actually doing that whole process that I just showed you, which is these calculations and the chain rule. Make sense? All right, so that's basically the background. Now let's move on to the next example. All right, so I'm going to create a new notebook for this one. And we're going to train a model kind of from scratch to basically learn how to predict Fahrenheit from Celsius. One other thing I want to make a note of here is, so we get that value, right? So let's actually go back to this idea here. So we get this value, like, let's say like 64 or something, right? So what do we do with that value? So we're going to see how it physically works in the code, but intuitively, I'm going to use a very simple example here of the information that you can assume this gives you. So this is the classic example that you will see for MSE, which is this one, the optimization chart. Okay, this is not what the actual neural network loss looks like, because that's not going to be quadratic. Like, this is a nice shape, right? A nice function. It behaves really nicely. But in reality, neural networks are going to have a whole bunch of these, a whole bunch of curvy things. So the intuition, though, that I want to give you is that when we did that process of the derivative to calculate that 64, think of it as you were calculating the value of, here at that point in time. Just think of it intuitively like that. So it's called stochastic gradient descent. So gradient, like in a mountain, going up or down. Do you guys see that? So basically what you can think of is that it's giving you at this point in the graph, in that function that I created, right? What does this line look like? So is it a line going down, or is it a line like this or like that? And what that gives you is basically intuitively, you can think of it this way. If I'm here, right? If I'm here at this point, the graph would tell me to go to the right. Do you see that? Because you want to step down. If I'm at this point in time, then what should it tell me? To go left. Do you see that? So it goes over here. So intuitively, this is what everyone will say. This is where the name comes from. But it's really that process that I just told you about that gives you this information. Do you guys see that? So imagine that this curve is like that set of equations. Taking the derivative of it is like getting this line here. And therefore, by the shape of that line, you know which direction to take. Imagine, for instance, that at this star here, this line that I drew here was like parallel to this line. So then there you could say that the value of that line is 0. And if the value of that line is 0, and you're also at the star already, what should you do? Should you go to the left or the right? Or stay there? So you should stay there, right? That's the value. So taking intuitively, you can think of as taking the derivative of the function tells you that, this line appears here or appears here, or if it appears tangent to this star, but parallel to this axis, then basically there's nowhere else to go. You see, it's got and mathematically it would have like a 0 value. Think of it that way. And so therefore the model, doesn't need to go anywhere. But if you're over here, then it's going to give you a line, right? And it's going to tell you, okay, you're over here, you still have more gradient to go. So keep going down. Do you guys see that? Now the learning rate, you can think of as the step size, because we're about to use a learning rate. So what does that mean, the learning rate? It means that if it's a small step, you would just like very small little steps going down. It's telling you to go down, but you go down very small steps. If you have a very large learning rate, boom, boom. What if it's a huge learning step? You're going to do that and never actually hit the star because the step is too large. Do you see that? So that's basically what's happening, and that's the whole intuition of this process. Keep in mind that neural networks will not have this shape. They may have more of a mountain range with several valleys. So some will be deeper than others, and depending on where you initialize your weights, you may never reach the deepest value in that set of curves, okay? But anyway, so that's kind of the background that I wanted to touch on this. So now let's look at the code. So I've created this new example here. I'm going to rename it. This will be temp Celsius to Fahrenheit. And we're basically going to train this model, but kind of from scratch. So I'm going to take the ideas of the previous thing and just add a little bit more to it, okay? And then eventually this will look very familiar to the training that you've already done. Okay, so I'm going to go back to my Jupyter here. All right, so we're going to go to this. So the final one is this one, Scratch Optimization Learning, okay? So we're going to train this model. It shouldn't be that bad. We don't need any data. I'll create some random data, basically, but actually not random. We know temperatures, right, of Fahrenheit and Celsius, and then we should be able to test this model. So we looked at differentiation, right? We looked at having some functions, taking the derivatives of it, taking the chain rule, and then the intuition, right? That it's telling you if you should go left or right on some curve, right? We've looked at that. Now we're going to look at actually training the model. So I'm going to use here a simple equation, y equal wx plus b. So I'm going to create here. So you can see this is actually a linear model. It's not even going to be like, it's not going to have activation functions. It's not very deep. Obviously, this is where we would start to add the layers that you guys already know how to do from the first third of the semester, right? Where you've already done that. So let's proceed. So using a linear function such as this, y equal w plus x plus b, we're going to train this model to predict temperature. So X will be Celsius, let's say. I don't know which unit we'll use, either one. Celsius, and then this should be Fahrenheit, for instance, right? So what is a Celsius? Celsius is like 32, and that should be 0, right? Yeah, right? 212 should be 100 or something like that, right? So work it out. Work out some problems, and we'll test it at the end. But what we need to learn is this W and this B, okay? This is what we're going to try to learn, basically. And we're just going to use the machinery of PyTorch. But the underlying thing is that it's going to be calculating these gradients of this function. All right, so let's go ahead and do that. So I'm going to grab my 3 libraries here. Oh, so I'm going to actually close this because I don't need it anymore. All right. So let's add the libraries. All right, so it's thinking there. Okay, that's done. Now, oops, I'm going to close this. Okay. Now I'm going to create some data here. I will change the name of this. So let's see. 0.5, no, 0 is, this is probably 0 to 35. That makes sense, right? So 32 to 0. And then what's the temperature? -4 to 21. Yes, very cold. So this should be Fahrenheit. Like that, right? So I'm going to just, one is Celsius, one is Fahrenheit. And I'm going to train, obviously there's an equation, that somebody discovered for this, right? But we're going to train, instead of using the equation, we're just going to train a model to do this. Okay, so I'm going to go ahead and hit run there. So now we can instantiate these as tensors. Initially, they're just Python lists. So it's going to be TC and TF. And this is going to be now just TF. And we can print them. Okay. Oh, yeah, sorry. So this should be TF and TC. Right, so we have basically our data to train our model. We have our X's and our Y's Okay, so now we're gonna proceed. So remember, we're gonna try to build a model here. So let's go ahead and plot our data. So X labels should be TC and TF. All right, so that kind of gives us an idea. So if it's 60, what's a Fahrenheit? Yes, in the 60s. So that's about like 18, maybe 80. It's really hot, like over 25, right? And so on. So you can see basically our data is, connecting Fahrenheit to Celsius, okay? And the scale, I think, is correct, right? So 20 Fahrenheit is pretty cold, yeah. All right, so now let's keep going. So here we have the model. So notice this is the inference function. This can be replaced by, this is a linear model, like a type of a linear regression, one of the traditional models, but you can easily start to add activation functions, a multi-layer perceptron, whatever you want in here. But in this, I'm just going to copy this function. All right, so notice that this takes TF. So this is predicting Fahrenheit. Sorry, it's given Fahrenheit and predicting Celsius. That's going to be the goal, okay? Notice that there's this W and B. So this is a new thing, right? A little bit different from what we did in the first third of the class. And that's because I'm kind of going from what I just showed you with the derivatives to like the final thing that you've seen on how to build the neural nets. So I'm kind of passing the W and the B separately here, which remember, these are going to be this W and this B, okay? So in this equation that you see there, that's that W and that B. Those are the parameters that we want to train, okay? The parameters that we want to train. So I created the model. Let's run it. Okay, perfect. Now we need to create the loss function, right? And so far we've stressed a lot MSE because it's the easiest and most intuitive to understand. We still need to do cross entropy. We'll do that a little bit later in the semester, but that would be the last one that we would cover. So let's go ahead and just copy the function. So I believe in the past, we just used f.msc or nn.msc. We actually used the torch function. Here, if you notice, we're kind of using more like the equation itself, right? So what's happening here is this model will predict y pred, right? And then you're also going to give it y real. And so you're going to take the difference between y real and y pred, square it, and that's basically a tensor of several samples, right? So if we're giving it like all the data at the same time, so then we just take the mean of that. We covered this last week, right? When we were looking at batch normalization and those things, this is similar. We're just, it's not a normalization in this case. It's just a calculation of the differences, but we're gonna take a mean of it. Does that make sense, guys? And that's how we can calculate the loss for a specific batch of data. Now, this is a very simple example. I'm not using anything like randomization or anything like that. Just going to give it the same data set every time. But that's my loss function. This y real and y pred is that connection that I did in the other Jupyter, the previous Jupyter notebook that we covered. Right, so the E at the end, right? So this EZ minus T squared, that E in the computational graph just grabs the difference between the two. And that's also being implemented in the PyTorch code. Okay, you can see y real, y pred, where y pred would be the output of this one. All right, so we have that loss. Let's run it. All right, so it's already in memory. And now we can proceed to do the training, basically. So here is where it gets a little bit more complex. So this is going to be my training function. Okay. Okay, so this is where we have, this is a little bit different. It's the same as before, but just a little bit more, more detail here. All right, so let's take a look at it. So this is the training loop. Notice that what the training loop will return is actually the parameters. Which parameters? W and B of the linear model that we're trying to train. You see? So let's look at the logic. So I'm going to provide the number of epochs, the learning rate, which is that step that I was talking about, the params, and then I'm going to provide TF and TC. So I think I had let's say 10 examples of the Celsius and the Fahrenheit. So I'm going to pass that data to the model to learn. So here in the learning process, I have, I'm just going to change all of these. Okay. So now let's take a look at it. So I have a for loop for epoch in range to n epochs. So that means I'm just going to repeat this, let's say 100 times. Notice that I do this if parameters grad is not none, params.grad.0. You had seen this before. There were 3 steps whenever we were training, right? Zero out grads, backward step. Those 3 things you always do. This is like what's happening is every time that you calculate the derivatives, right, in the training loop, they stay in this thing called params.grad, in that grad parameter. So they're basically accumulating, but you don't want them to accumulate for what you're doing, so you zero it out. It's like if you don't zero it out, then it's going to take what you calculated before and add the new thing. And then the next time it's going to take those 2 and add the new thing. So you have to basically zero it out. That's just, I don't know, it's a PyTorch weird thing that you just have to do. It works that way. All right, so you have to do this. So zero it out. Then after that, in the training loop, notice here it is, you're going to give it the Fahrenheit data only, right? And notice that I'm also giving it this thing called params. What is this thing params? Is this tensor here? It's actually going to be a pointer to memory that will point to the W and the B. We need to define that because I'm treating it separately, right? Just so that you guys can see that we're going to be updating these kind of indirectly to show you the functionality of .grad. That's the whole point of it. Just like we did in the previous examples where we were calculating the derivative and then printing that A.grad, B.grad, and whatever it was. So it takes the Fahrenheit data, it takes the parameters, which at the beginning are just some random value, and it's going to predict. So you give it a Fahrenheit, it predicts a Celsius. That's this Y-pred here. This Y-pred then gets compared to the real Celsius, which is TC. So actually, I'm going to give it like 10 Fahrenheits. It's going to predict 10 Celsius. And then I'm going to compare those 10 predicted Celsius to the real 10 Celsius. Okay, so that TC and Y-pred are passed to the loss Fn. We've already defined loss Fn, which is this one over here, if that makes sense. Okay, so now I have my loss, this one, and this is equivalent to that E that I had shown you in the previous example. So that means that I want to take the derivatives of it, the chain rule. Well, how do you do that? You invoke backward. Before, right, we were invoking z dot backward, remember, in the previous examples. Now we're invoking loss dot backward, but it's exactly the same thing happening in the background. Okay, the exact same thing. So once I do loss backward, then what do I have? I have for my params dot grad, just like I had before, A dot grad, B dot grad, right? I have the values in there. So basically they're in the computational graph. I run backward, calculate the derivatives, and they are stored somewhere, right? And now I'm going to use them to update my model. So you can see this, you create the computational graph with these 2 things. Then you grab the node, just like before, you calculate the backward, and then you're going to do this. This is the update rule, okay? So if you notice, we didn't do this before, right? So in the past, so this is a good exam type question, right? Make a note of this. During the first third of the semester, when we were doing the PyTorch examples, what did you guys use here? Do you remember? Optimizer step. Very good. So you guys did that. Optimizer step, right? And you're like, okay, what is that? Who knows, right? Well, that optimizer step is actually this part here. The update of the weights, okay? So in the first step, we calculate the derivatives. Those values are now stored in these variables W and B that have a dot grad field. And then all we have to do is we take params equal to params minus learning rate times params dot grad. That's it. That's the magic of PyTorch. But we didn't have to like hard code this. So anyway, we create the graph, we take the derivatives, the whole chain rule thing. This is, so I'll say calc derivatives and derivative and use the chain rule. Like in previous example, okay? And then once you have that value, those values get stored in the variables that we said requires grad, which will be the values stored in params W and B. This is actually two values. It's a vector. So then now you just do params equal params minus, in this case, it doesn't matter minus plus because the learning rate actually will have a sign that you care about. So let's say this learning rate is, I don't know, let's say it's 0.01 times those values that you calculated there, whatever they are. Let's say this is 23, something. But you get that every time with respect to this equation that you take this backward calculation. So you go to function through the derivative to the derivative function, and then you get the value of it. All right, so I'm going to get rid of this. This is just for illustration. And that's it. That's it. So this no torch no grad is because you don't want to update the weights except through this method. Okay, so that's why you set that up. And then now we just print basically every 500 or so epochs the loss, and the loss should be going down if this worked, okay? All right, so I'm going to go ahead now and save that, okay? So you've seen it in action. So now we should be ready to do the training. So I'm going to go ahead and call the training loop. Okay, so let's take a look at the training loop now. So it takes 100,000 epochs, right? So that's a lot. This is the learning rate. Notice the params are initialized here. And what are they? They are a torch tensor of two things, where one is going to be W, the other one is going to be B. And we specify this parameter, which is really important, requires grad. Just like I showed you in the previous example, so that whenever we take that backward step, we calculate the equivalent derivatives of it at that point in time, and boom, we know what to do in the update rule. And that's it. In the simplest form, this is how it works to train deep learning models, even, GPTs and so on. All right, so the data here should be TF. All right, so let's go ahead and run it. Okay, and there we go. Let's take a look. So if you notice, the loss is going down, right? And that's a good thing. It's printing every 500 iterations. So see, it's going down. Going down nicely, actually. Any questions, guys? And this should be, you should understand now how to train your own machine learning model from scratch. The architecture can be as complex as you want, and it's not an issue, right? All right, so let's take a look over here. Almost done here, maybe. So it's at 6, 5. All right, well, it's doing that. So it's going to continue. You can see here, it gets down to about 3.7. Result is what? It's the parameters, the weights, W plus B, because that's the way that I kind of did the function. If you look over here, the training loop, right? It just iterates over time. Params, W and B are just like a global variable. And then when it's done, it returns it. Why is that relevant? Because that's really important in today's world where you train a chat GPT. Imagine that this was a chat GPT. It took $8 million and 6 months to train. But really what you want is these params. Obviously, you wouldn't just have 2, you'd have millions, right, of parameters, or billions even, right? And that's what gives the intelligence to the network, because that W and B is what it uses to predict. All right, so I think it finished. That's really good. It arrived at 3.37. Okay, so that's good, similar to my example. So now we're just going to go ahead, and result should contain the 2 W and B. There it is. And it basically learned these parameters, right? That 0.48 is really like, you have to multiply your Celsius times 0.48 and then have this bias of minus 14 to arrive at the other temperature. Do you guys see that? That's the laws of physics right there, right? Or chemistry or whatever it is. Okay, so now let's go ahead and think about it. So I'm going to grab my model. So I have a reference thing here. So I'm going to do a prediction, right? So why can I do that? Because my model works this way, right? The architecture of my model takes in 3 parameters. So let's take a look at my function. So my function model takes in TF, which is the Fahrenheit temperature, and then it accepts W and B. You can pass several things by putting that star in there. It's like a pointer to a thing. So, and then the W and the B are basically used in the equation, and then that's it. Okay, so let's go ahead and try it out. We'll know if it works because we know the conversion. So in this case, I run it. Oh, yeah, I should print it. My temp. $33. So 99 degrees Fahrenheit. Is that close to 33 Celsius? Yeah. Give me another value. Like, what's another one? 32. Thank you. So 32 should be what? 0. 1.18. So close. It's not perfect. I mean, the equation might, but that's neural networks for you. Maybe how do you get that extra? Maybe, add some, this is a linear model, right? So you'd have to add an activation and so on. Does that make sense? Yeah. All right. So anyway, so that's what I wanted to show you. So look at both. You have to understand both examples today, right? The whole point of it was to show you what's happening in the background, what step and backwards are, right? So on the exam, you can expect questions like, explain what's happening when you do dot backward, or when you do dot step. Step is the update, and backward is that idea of calculating these derivatives that give you an insight into how to update the weights, basically. And you have seen that because that is actually literally happening here. Okay. All right. So Yeah, so we tried a few things and we printed out the model, and that's kind of the background that I wanted to cover as far as neural networks and how they work. I wanted to give you some insight, especially into backward and step and the chain rule. Now, again, will you be coding your models doing the update directly? This one here, no. You will just use dot step, right? And you saw that dot backward. We'd have to do this by hand, and you'd never be able to train anything that's way bigger, bigger than this. Okay? Yeah, please go ahead. Do you have a? Okay, you.
Really, I think the calculation part is like we have conversion formula.
Mm-hmm.
So like if we give the formula, it will give the exact value. Right?
Yes.
So
So why is this stupider than the formula? Is that your question?
not exactly that, but are we what are we trying comparing it with the actual values?
Mm-hmm.
Like but giving the feedback to the model with the using the formula.
Mm-hmm. I think I understand you. So why, instead of giving it some data as I did, why don't I just hard code the formula? And then every time it's like predicting, give that to the formula, get the real, compare it, and
compare it
and train it, and train the formula, basically. Yeah. That's actually a really good question. Actually, that's a really good question. Guys, over there. Why that? Because, yes, in that case, we know the equation. But really, there may be other situations where you don't actually know the equation. What will you have? Only observations. So I'll give you the classic example of this. Kepler. Do you know who Kepler is? Kepler is somebody famous in that, there's that sequence of Galileo, Kepler, I think, and Newton. So Kepler figured out what? The orbits of the planets. Now we have well-established equations for that. I mean, in fact, space is one area where you don't really need to use machine learning, right? NASA and all those, they built all these systems just on equations because the trajectories are very predictable, right? You don't need machine learning. So, but how did they figure out those equations? Kepler and people before him collected all this data, observations about the stars. So what is that? That's actually equivalent to this. So this is kind of what Kepler had, if you will. And then Kepler, in his intelligence, figured this out and probably won a Nobel Prize, or should have, right? Yeah. Nowadays, AI, hopefully, is going to look at healthcare data like this, or physics data like this, or chemistry data like this, and figure out new equations that we haven't even thought about. And then hopefully we'll get new discoveries, right? So that's the whole point of this. You guys see that? So that was a good question. Yeah, I like that question. Sometimes you don't have the physics of something, like what's going on inside, right? You don't have that. Yeah, you don't have it. Yeah. Good question. Does this make sense, guys? So this is kind of background as far as neural networks. I mean, this is it as far as what I'll cover in terms of background of neural nets. The only other thing I will cover a little later is going to be cross entropy. So that's the classification side of, and that's more on the focus on that loss function. All right. And then we'll cover a few traditional methods still. And then the big thing that's next is CNNs, right? So I'll cover CNN starting next week. And I'll try to build as far as stable diffusion. And the nice thing about that is I'll be linking text and images, in stable diffusion to give you the idea of how that works. Okay. So it's 6:10 right now. So this is a good stopping point for this lecture. And in the second half of today, I'm going to do unsupervised learning. So that's kind of like a separate topic. So I think let's take a 10-minute break now from 6:11 to 6:21. And then when we come back, we will look at those ideas of unsupervised learning. And actually, we'll start to think about embeddings also in text. Okay? All right, so I'll stop this video and we will start again at 6:21.